So, things are going smoothly. Let me know again if you need anything or have any questions. Main goal for today is to talk about electrical power, namely calculating the electrical power that a component of a circuit uses, but additionally being able to utilize information about electrical power to help understand how actual electrical systems that we use in the real world work and kind of how power bills are calculated, which I hope is going to be something useful for people to understand moving forward in life. That's the main goal for today, and that'll be the last piece of Chapter 17 to cover. Once we're done with that, tomorrow can be a good morning. Hope you're doing well. Let me reiterate the last few points I made then. Today we're going to be talking about electrical power in a circuit and how to use that knowledge to calculate electrical bills. That'll be the last material for Chapter 17, and so tomorrow will be kind of a free form, come in as you have questions homework day. Excuse me. Next week, we're going to be looking at various topics related to magnetism. I'm kind of going to be combining a bunch of different chapters from the textbook that the course is based on together, just to kind of hit on the more important parts of magnetism. And then after next week, after the combined kind of composite magnet chapter next week, then we'll be moving on towards Test 2, which will be about all the electricity and magnetism stuff that we've covered this summer. So, again, let me know any questions, needs, concerns that you have. Be working on the homework and quizzes as you go, or following along with video lectures. Give everyone a second. If you have questions now, you can submit them. I'm going to make sure that the slideshow for today is working correctly, and then we'll get started. All right. So, some brief review. We've been talking about current and resistance in circuits. Voltage is the pressure that pushes electrical current through a circuit, namely specifically through the resistors in a circuit, which offer literal resistance to the flow of electrons. How you arrange the resistors within the circuit does contribute to how they add up together, what the sort of net effect of the circuit is. Yesterday, we specifically covered how different arrangements of circuits can result not only in different total resistances, but also in different patterns of how the current and how the voltage gets split up and shared across the circuit as a whole. And today... No. Sorry about that. Today we're going to be looking at electrical power, which is going to be a measurement of how much energy specific components of a circuit are utilizing. When we talk about... When we use electricity, the purpose of it in our machines is to carry energy from place to place. Forgive my dog. Penny. Pan, come here. Sorry about that. When we build machines that use electricity, the point of the electricity in general is that it can transport energy from place to place, or it can be used to store energy in a battery that can be utilized later. Power, kind of like how we've used power several times across Physics 1500 and 1510. In 1500, it was defined as the rate at which work is done, the rate at which energy is used. Within this very class, we talked about power as could be used to describe the rate at which thermal energy flows from point A to point B. Electrical power is kind of continuing on that trend. Electrical power is the measurement of how much energy a certain electrical device uses per unit time. It could also be used to describe how much electrical energy a certain amount of current transports from one point to another. So, the original formulas about power, let me add them in with my tool here. The idea of power representing energy over time is still true. That formula still works. P equals joules over time, work over time, energy used over time, energy transmitted over time. All that logic is still true. That formula still exists. It's still useful. We're going to be utilizing it together here. Our new formulas are designed to tell us how much power is currently flowing through a specific component of a specific circuit. Again, power here representing how much energy that piece of the circuit is drawing, how much energy it needs every second in order to stay active. Again, power is defined as energy per unit time. Power is measured in watts. So if you were to go to the store, buy just even a light bulb, everything that is powered by electricity has a wattage rating somewhere on it. It might not be immediately obvious what the wattage of like your computer or your TV is. That information does exist if you check the manuals far enough. But usually light bulbs have their wattage listed pretty prominently on the package. They used to be sold or classified based on their wattage for that, and so that's why that information is still there. If you bought a 60-watt light bulb, so 60 watts would equal 60 joules per 1 second. The old formula for power, the original definition of power, P equals energy over T, tells us that a 60-watt light bulb needs 60 joules of energy every single second to be active and fully functional. If the circuit you plug that light bulb into isn't capable of giving it 60 joules per second, the light bulb won't perform correctly. It'll be dim, or it might not turn on at all. And this is actually true of all electronic devices. They all have a certain wattage. They all need a certain amount of power to stay on. This is one reason why sometimes like if you've got a lot of things plugged in a single room, like living room or kitchen area that has active TV, active fan, active lights, maybe you're running the microwave or something, and someone plugs in another machine into the wall, maybe running a vacuum cleaner, I think is the most common example where people see this. The lights in the room may dim, or maybe certain devices just turn off when you turn the vacuum cleaner on. Because by adding the vacuum cleaner into the system, it starts taking energy out of the system that was previously going to other things. And if those other things aren't getting their required amount of joules per second to meet their wattage, they either dim and don't work quite right, or they might even turn off completely. So that's why that happens, and that's what the number of wattage represents when it comes to electronics. It's the energy per second it needs to remain active. Even humans have a certain wattage, if you think about it. We need a certain amount of energy from food in order to stay awake and be able to do things. So that's the old formula for power, which is still good and still useful, and we are going to be using it. But there are some additional formulas for power that allow us to specifically calculate how much energy or the wattage of a specific component of any given circuit, just with the information that the circuit would probably already tell us. These first two lines here just exist to kind of show how the formulas were derived. The important line to pay attention to is this one down here. Power equals current times voltage drop. The amount of energy that any given electrical component in a circuit is taking out of the current per unit time is equal to the current flowing through that component times the voltage drop across that component specifically. So if we back up to some of our examples from yesterday, Let's look at this 10K resistor in this 9-volt parallel circuit. Yesterday we determined this resistor would have a 9-volt voltage drop across it because it's arranged in parallel. So resistor 1 right here has a 9-volt voltage drop, and we know that there is 0.0009 amps of current flowing through that particular resistor in this specific circuit. Using that new power formula, P equals IV, with this voltage and this current, we'll be able to determine how much power is drawn specifically by that resistor in this total configuration. Similarly, if we instead looked at the 2K resistor right here, it has a 9-volt voltage drop, but it has a different amount of current running through it. So it would be drawing a different amount of total power from this particular system because it has its different resistance leads it to have a different current despite having the same voltage. So current times voltage drop tells you how much of the system's energy gets absorbed by that particular component every single second. The bigger the voltage drop, the more energy kind of gets eaten up by that specific object, by that specific resistor in the circuit. Now, P equals IV is not the only way this formula can be written, because we have Ohm's law that is further able to specify the relationships between voltage, current, and resistance. So P equals IV, but additionally true, V equals IR. The voltage across a component equals the current running through that component times its own resistance. Some very smart people were able to combine these two formulas together to create these other two parts after this first set of equal signs. So P equals IV, but additionally true, P equals V squared over R, the voltage drop across a resistor squared, the voltage drop across a resistor squared divided by its own resistance would be additionally equal to the current running through that particular component squared times its own resistance. All three of these different parts are all just different equally valid ways of calculating the power draw of any specific component. They're all pretty much interchangeable. Which one you use just kind of depends on what aspects of the circuit you know or you think you best have an estimation for. If you have current and voltage, you'd use the first one. If you had current and resistance, you'd use the last one, etc., etc. So, just with the information that we kind of already have from studying circuits, V equals IR, it's not much of a step further to be able to calculate specifically the power drawn by any given part of a specific circuit component. And again, that power draw just tells you how much energy it's absorbing every single second. Higher the power, higher the wattage, the more energy that particular piece is constantly drawing out of the current, out of the system every single second. It's hungrier, basically. So those are the, I guess, three formulas to use for this for this sort of genre of power questions. There's the old power equals energy over time formula. There's P equals IV and all its permutations. And there's the original statement of Ohm's law, V equals IR. Check my notes real quick. Okay. So, let's look at some examples utilizing all of this information. Whoops. So, when it comes to power, I'm going to try to phrase the examples in terms of how it would come up in kind of your common life using electricity in a household. So, as an example then, a typical US wall outlet has an output voltage of 120 volts. That's kind of the standard voltage across the United States, and most countries use similar amounts. Most modern televisions have a power rating or power requirement of 60 watts when turned on. First things we're going to calculate are how much current does such a TV draw, and what would that particular TV's internal resistance be? If that television was treated as just a simple resistor in the circuit of your house's diagram, what would its equivalent resistance be? What's the resistance of every piece of the TV added together when you run electricity through it? We'll focus on the second part of the question after we answer the first part. And I'll kind of put a dividing line between the first part's work and the second part's work. So, US wall outlets have a power rating of a voltage of 120 volts, which is a lot. Like, that's a pretty, considering most batteries you'd buy in the store are like 1.5 volts or maybe 9 volts. 120 is a lot, actually. Most machines, most devices, when you plug them in, if you've ever noticed that like your laptop's power cable has either a big chunky plug or a big chunky rectangle brick somewhere along the length of its cable, the purpose of that particular block is basically to modify the incoming voltage to what the device actually needs, because not every device actually needs 120 volts to work correctly. But we kind of set it to 120 volts because it's easier to scale it down than it is to scale it up. So wall voltage is higher than is required because, you know, each device has a little brick on it that can scale the voltage down to whatever the machine needs. But today we're just going to use the full 120 volts. So our TV is going to be powered by a voltage drop of 120 volts, and the TV in question has a power rating of 60 watts. How much current does this TV draw when on, and what is the TV's internal resistance? Looking at our new power formula, P equals either IV or V squared over R or I squared times R. We have several options that we can pursue here. First thing we were asked for is current draw. We know power, we know volts, we want current. So for the first part of the question, we're going to utilize this first piece, since it has the two things we know and the one thing we want to know. Power requirement of 60 watts will equal current times our voltage of 120. That's going to give us a current draw of 0.5 amp. This might be a little unrealistic because, again, 1 whole amp is pretty deadly, 0.5 amp is pretty deadly, so this might be a little unrealistic, but for this particular question, this is the numerical answer. Be careful with electricity. So that's the current draw of this particular system. Next question is, what is the TV's internal resistance? So we now know P, I, and V, so there's several formulas we could use. I, for the work that I did right here, used P equals I squared times R, so the same power rating of 60 equals our current draw that we just calculated of 0.5 amp squared times resistance. This is again going to tell us the effective resistance of the TV as a whole if you treat it as a resistor in the circuit. And that would give us 240 ohms. So parts of this formula are all interchangeable. Different parts will just be more or less useful depending on what things you know and what things you want to find. Now the second part of this question, which I haven't read out loud to you yet, is the part that might be a little more useful for calculating your electrical bills. And it's one reason why I wanted to cover it. In the United States, we bill, your energy bills are in terms of like a number of cents They charge you a number of cents per kilowatt hour of energy that your house uses. Kilowatt hour is a new unit. We haven't used it before, but it is a unit of energy. So joules as a unit of energy measure the same thing as the new unit of kilowatt hours. 1 joule is not equal to 1 kilowatt hour, but they are both measurements of energy. And I can prove this by, if you look at the unit of a kilowatt hour, it's literally watts times hours. Watts equals joules per time, so multiplying watts by time just gives you a unit of energy. So, kilowatt hours is a unit of energy. Your house gets billed a number of cents per unit of energy that you use. And the trick to calculating how many kilowatt hours specifically that your house uses is, like, the definition of a kilowatt hour is literally 1 kilowatt times 1 hour. It's the energy that a 1 kilowatt appliance, an appliance with a wattage of 1,000 watts, uses if it's turned on and used for a total of 1 hour. So 1 kilowatt hour is literally a 1 kilowatt appliance times a 1 hour runtime. So in general, to find the kilowatt hours used by a machine, you want to take its wattage, convert it to kilowatts, and multiply it by the amount of hours that it's active. We're going to utilize the TV that we just looked at in this particular example. 1 kilowatt appliance active for 1 hour uses 1 kilowatt hour of energy. If your power company bills you 10 cents per kilowatt hour, that's a fairly common charge for electricity in the U.S., ignoring peak hours. Peak hours are their own separate ball of wax, but normal hours during the day, 10 cents per kilowatt hour is pretty standard rate. How much does it cost in an electricity bill to watch 1 hour of TV with this specific 60-watt TV in question? So, 1 hour using a 60-watt TV, how much does it cost to power it? So, we know 10 cents per kilowatt hour. If we find the number of kilowatt hours of energy this TV would hypothetically use, we can figure out how many cents that would take. So, our 60-watt TV converts 60 watts into kilowatts would be 0.06 kilowatts times 1 hour equals 0.06 kilowatt hours. It's not a lot. The power company then bills you 10 cents per kilowatt hour, so 10 cents times 0.06 gives us a grand total of 0.6 cents per hour of watching TV. That's 0.6 cents. That's less than a penny. This is, again, ignoring peak hours. Depending on where you live, there are certain times of day where electricity gets more expensive. Outside of peak hours, most appliances like TVs and light bulbs don't actually cost you that much. Light bulbs have a similar wattage range. Most light bulbs tend to be somewhere between 60 to 10 watts. So light bulbs cost less to use than a television. I'd say most computers, like a desktop computer, might be 100 watts. So not that much more expensive to run. If you're wondering, like, what the biggest... If it doesn't cost that much to use a TV or light bulbs, you might be wondering what actually contributes to power bills. Like, what actually has the potential to make them so high if 1 hour of television is less than a cent. For one thing, most power bills are billed over the span of a month, so multiply 0.6 cents by however many hours of TV you watch a day, and then multiply that by how many days are in a month. Like if it was 2 hours of TV a day for 30 days, that would be 1.2 cents times 30, but that would still only be like 40 cents. Your TV and your light bulbs don't contribute much to your power bill. The things that contribute most to your power bill are high wattage devices that are always running, that are just always plugged in and always on. And hands down, in most homes, the two biggest machines that are doing that are your air conditioner or heater, depending on the season, and your refrigerator. Literally, they're always plugged in, they're always doing something, be it actively cooling or in their recharge state. Those are easily the two biggest power draws, just hands down. Leaving the lights on really doesn't have much of any effect. And if you've ever had a relative or a guardian get on to you about that, here's the math to kind of prove them wrong. If you've ever had anyone get on to you for leaving the TV on or leaving the light bulb on, here's the math to prove that is not their biggest concern. I think some fridges and air conditioners might be up to have a power rating of 1,000 watts or so. I think washers and dryers are pretty watt hungry too, which is why they have such big, very customized plugs. Water heaters can be kind of sneaky too, depending on the design and depending on how much hot water you use in a month. So I'd say those are the 5 things to be most concerned with. Top 2 is definitely fridge and air conditioner, followed by water heater, washer, dryer. So, fun facts for your future whenever you start paying your own electrical bills. Questions, comments, concerns thus far, please let me know. I'm going to backtrack a little bit just to look at some of the circuits we worked on yesterday. Our power formulas can be kind of like how we used V equals IR to examine this circuit as a whole, find the voltage in the circuit as a whole, the current in the circuit as a whole, the total resistance of the circuit as a whole. And then we could also use V equal IR to look at specifically the voltage drop and the current through specific resistors. You can use the power formulas here in similar ways. You can use the power formulas to figure out how much power an entire circuit uses if you use the entire circuit's voltage, current, and resistance in your power formula. Alternatively, you can also use the individual voltage drop, current through, and resistance of specific resistors to find the power draw of specific components of the circuit. So very versatile formulas, and they go hand in hand with Ohm's law and the stuff that we've been doing the past couple of days. It's just kind of the next logical step from there. Figure out the voltage across something, the current through something, its resistance, and how much power it's drawing using the same information. So you can find power draw of the whole system. You can find power draw of a specific part of the system. I wanted to point out some power type questions that these are not the exact ones from your homework, but these are the kinds of questions that can show up on WebAssign, the kinds of questions that WebAssign might ask. Just kind of talk about what information one might use for a few of these. First, we'll look at this. First, this one up top is just a pure power question. 9-watt light bulb or 9-volt lamp produces the same illumination as a 45-watt lamp. How much does the energy efficient lamp save you over 105 hours of use? Assume 0.08, that would be 8 cents per kilowatt hour. That's a pretty good rate. To work this one, you basically want to figure out how much more energy the higher wattage lamp uses. Namely, in this case, 45 minus 9 is an increase of 36 watts. So 36 watts converted to kilowatts times 105 hours times 0.08 dollars per kilowatt hour would give you a total difference of 30 cents So, across a whole month, changing the light bulbs of your home can help you save energy, but if it's just a single light bulb, you might save 30 cents. If you change every light bulb in your house, though, assuming you've got like 10 of them, that can start to add up over time. But that's how you look at that specific question. Next example from WebAssign to look at: a high voltage transmission line with a resistance of 0.34 ohms per kilometer carries a current of 950 amps. Again, that's a lot. The line is at a potential of 750 kilovolts at the power station and carries the current to a city located X far away from the station. What is the power loss due to resistance in the line? What fraction of the transmitted power does this loss represent? This is kind of more just an example of problems that electrical companies face in real life that can affect end users. Every single thing has resistance. That includes just the normal copper wires we use in lab. That includes the transmission cables that power lines are made out of. Everything has some amount of resistance. You try to make the wires of a machine out of material that has as little resistance as possible, because you don't want power getting eaten up by the wires themselves, but it's kind of something you can't really avoid. It's basically the electrical version of friction. You can't avoid individual components, individual wires even, having resistance, eating up power in a circuit that then is power that isn't going to the actual end source or isn't going into the actual functioning parts of the machine. Since wires have resistance, and since you can run current through them, one of the formulas for power tells us P equals current squared times R. If you run current through something with a resistance, it eats up electrical power. The wires in a machine, even if their resistance is incredibly small, the fact that they have resistance means they take up some of the machine's power. And this is one reason why the wires eventually heat up and eventually need to be cooled off before they melt or before the machine breaks. Everything that draws power is gaining energy from the electricity. And as a result, it eventually warms up. Because absorbing any energy, inevitably some of it is going to turn into thermal energy. In the case of the energy absorbed by a wire, all that wire can really do with that energy is just warm up, because the wire can't really do anything by itself. It just gets hotter as a result of absorbing this power. So power lines, or just the wires in your phone, have a resistance and they eat up power as a result of that. For this specific question, we know we can figure out the resistance of a certain length of this transmission cable. We know how many ohms it is per kilometer, and we know how many kilometers long it is. So 0.34 times 156 would be 53 ohms of resistance. 53 ohms of resistance. We could figure out the amount of power lost by a 53 ohm resistor when you have either this current or this voltage moving through it. So that can tell you how much power is lost to that specific wire of that resistance. And you can figure out then what portion of the total power was lost as a result of that. You can determine how much energy is lost to your wires. You want it to be as low as possible. I think about 7% in this example is pretty good. It's just kind of annoying that we lose any of it at all. Again, this factoid is like the electrical equivalent to friction. We can't really avoid it. It's just always kind of rearing its ugly head to cause problems. And that is, I think, all of the mathematical formulas and concepts needed for Chapter 17. We've covered everything related to current, voltage, and resistance, and power. that you'll need to be able to do the homework and eventually the upcoming test and the quiz, by the way. So at this time, I would like to open the floor up to you if you have any questions about any of the concepts talked about today or this week, or any issues encountered on any homeworks or quizzes. If you don't have any specific questions right now, we can go ahead and call our daily break. I'll be here if you want to jump back in over the next hour with any questions. I do recommend be looking over the homework. And tomorrow will just be a drop in as you have homework questions day. Next Monday, we'll start chapter 18 and magnetism. Well, we'll start magnetism next week. The chapter number is going to be a little inconsistent, but we'll start magnetism next week. Might take a little longer than the week itself, but we'll get through most of magnets next week. We will also have lab next week. And sometime the week after that, we're going to start moving towards test 2, which I'll make sure you have access to review materials and you'll know the test date ahead of time. It'll be over WebAssign like the last one. I'm rambling a little bit for lack of anything else planned for today. So let me know what you need. If you don't need anything right this second, we can have our break. And if I don't see you again today, I'll see you either tomorrow if you jump in with questions, or Monday for magnets. See you then.